Hello and welcome back to Calculus 1, section 3.7 on the infamous chain rule. I mentioned few times, now this is important business, I mentioned few times that about 90-95% of derivatives you will ever take in all of your future courses are going to be chain rule, because vast majority of functions are generally composite functions. So it's very rare to see x squared used in a field, or even e to the x, or sine x. It's always some kind of modification somewhere, which means chain rule will kick in. The difference between the regular derivative and the chain rule is already known to you. We have to do a lot of preliminary work before we get into the derivative, but let me just give you an immediate idea. So the derivative of e to the x is e to the x, and then the derivative of e to the ax is a e to the ax. So as you can see over here, it was just a simple copy. You still have a copy here, but there is this extra a, and that extra a is obtained through the chain rule. So the goal for tonight is to learn how to deal with the derivatives of function composition. And to do that, we first have to talk about function composition. I did mention last time that you should review function composition, because without it, you won't be able to perform this most important technique at all. So let's talk about function composition. This is 1.7 in the pre-calc book. And I told you that that book is available free as a reference in the library or tutoring center. So you can go and take a look at the book and, also see through those concepts on your own. So function composition. You take a function and you plug that function into another function to obtain the third function. Technically, that's what it is. Now, what do we have? We have the idea of, everything that is around you has a function, and if it doesn't, it's garbage and you just ignore it, right? So if you think about your backpack and you think about let's say the folder with papers or binder or whatever, the backpack has its function, which is to carry your items, and then you have the items that you put inside, which have the function to do something. So if you have a bag, the backpack, which is filled with notebooks and books and things for school, you know that backpack is for school. But you can empty that backpack and put something else, and you are changing actually the function of the backpack. Because when you're the airplane with number of, few thousand feet away, it matters which backpack you pick up as you're jumping out, right? The camping equipment won't help very much if you jump out of the airplane with that backpack on your back, right? So, see, the function of the backpack changes by the content of the backpack, and the backpack's content has function, which is a parachute or a frying pan, right? So you have to, or a book, right? So you're going, what are you going? You're going skydiving? Are you going camping? Are you going to trip? It's clothes inside. Or are you going to school? It's all books. So that's where the idea is, that you are able to plug one function into another function and create a completely new function, right? The backpack will look the same from the outside, and it still has this overall function to carry objects inside, but you know very well that you are supposed to take the skydiving, right, backpack with parachute inside rather than your backpack with books as you jump out, right? See, I have to actually shut it off. So how do we do this mathematically? Well, I have a function f of x which does something, and I have a function g of x which does something else. So now I can create function composition. Now this is like a multiplication times, but it's actually open circle. It's not O. So you can't read this fog. It's not fog, because this is not O. Alright? It is F composed with G, which means that G is plugged into F. That's the meaning. And you can also compose G with F. These things are not commutative. And you will have G in charge and f of x plugged inside. So now, if I define f of x to be, say, 6x squared plus 3x minus square root of x, and I define g of x to be how about e to the x is fine. I can create function composition by plugging g into f. So it's going to be f of g of x, which is actually f of e to the x, because that's what g is. G is e to the x. So now, on the outside, I have 6 times, and this is supposed to be g, so it's actually e to the x squared, plus 3 times another e to the x, plus square root of e to the x. So what happened here is we replaced every x with g of x, and then every g of x we replace with e to the x, because that's what g is. So now, if you want to simplify this, you have it as 6e to the 2x, because exponent of exponent multiply, so x times 2 is 2x, plus 3e to the x, plus the square root of e to the x, and this is the function composition. So function composition is going to define these functions, and especially these, right, where you actually find the function composition. The next talk here, very briefly, is a talk about the I want to see. Yeah, I'll leave that for later. All right, let's go and take a look now in the very important part of decomposing a function, because that's actually what we are after: decomposing functions. We have a function composition that puts everything on a pile. Decomposing functions through factoring and splitting and all of these kind of things should be able to give us the clearer picture of the problem. But let's see an example immediately. So let's say I have f of x. I have y equals 3 ln x squared minus 2. What is the outer function, the shell function, and what is the inside? Well, first off, I don't have to really worry about this 3 to have it as another layer, because it's just a constant 3, it keeps multiplying, you can kick it outside. There are ways to deal with 3. So we technically ignore 3, all right, ignore it, not there. What I have here is the function which traps in another function. Do we all see that? Do we see that x squared minus 2 is trapped within ln? So who's the boss? ln is the boss, and that's the one that goes on the outside, and say ln x, and then the one on the inside is x squared minus 2. So now, oh, sorry, it should say f is 3 ln x. I'm sorry, 3 ln x, because we still have that 3 there. Now, recall that this x here will be replaced by g, and as soon as that happens, we got this, right? So we can do this. We actually need to be able to do this so that we can do chain rule. This is where the chain rule lives, right? In these types of problems, and then decomposition mentally done by you by that time, right, is going to help you with these things. Let's take a look at another example before we start calculus officially. Y equals, let's just do 4e to the negative x, and then times, I don't need a parenthesis, times sine of 50x, whatever. I should have known. I can put whatever there, it's going to work. So when you look at this, right, you should see a product rule, right? The only second layer functions are actually that 50x and negative x. Now this has these formulas have application. If you have the pendulum that it's swinging, it will eventually stop, and that's due to this, because this is the sine part is particular. It's pretty much the given oscillation, and the pendulum should go like that forever without air friction and all of that stuff. I need you to separate this in your head, that there is multiplication here. So this is a clean product between two functions. Now you can treat 50x as only 50x, right? As a function composition part. So I would have to do product rule on this one, and then employ chain here and employ chain there. So we'll see that procedure. So if I want to decompose this one simply decomposes f is e to the x, and g is negative x. This one decomposes into both function f is sine x, and g is 50x. So x will be replaced by 50x, and you will have your chain rule possible. That was a line all over the place. Oh, if I do this, it's going to start beeping, so it's fine. All right. So let's talk about the chain rule. First off, is anyone okay with onions? With onion? You all understand it's layered? Good. And we are going to be working through those layers. And we'll see that the number of functions that we have will be the number of factors that we obtain at the end of the problem. So these things are important. Let's first talk about the chain rule and the formulas and some of the theory that goes behind this. So let's talk about chain rule. So the first sentence in blood is going to be we use chain rule to take the derivative of function composition. So what is the formula that we are going to use? There are two forms, so you'll pick your poison. The first one is that the derivative of f of g of x is equal to f prime with g still plugged in times the derivative of g times the derivative of the inside. Now you can string this with as many functions as you want, but let's just practice two for some time. So this is what I have, and then good evening. And then there is one more version for chain rule that might make more sense. And this version will include the different notation. So the f dx will be df dg and then dg dx. And you see what would happen if I am to cancel these out. You get df dx equals df dx. Obviously we're not canceling it because we need them, but you see, so these are the two forms. And I think that your book is going right, this one needs to be special. The book is going out of its way to say, all right, use property number 1, property number 2, and so on. Who cares? Just get the problem done. Chain rule. So these are official formulas. Let's take a look at this in action. So say I have to take the derivative, and I'll explain these things as we get there. So d dx of say sine of x squared minus 1. We understand immediately that x squared minus 1 is g. I hope that everyone can immediately spot that, because that is plugged into the sine. Sine is the boss, therefore sine is f, and then x squared minus 1 is plugged into the sine, therefore it's a one onion layer below, i.e. not the boss. Right? There can be only one, we know that. From Highlander. Now I made a reference that probably predates your parents too. Alright. So let's go with this calculation. I am supposed to take the derivative, as you can see in the formula, looking at the red line. I'm supposed to take the derivative of the outer function, keeping g plugged in. Well, my outer function f is just sine x, right? But in technicality, is actually sine g of x. That's what it is. So what I'm going to do is I'm going to say, well, I know what the derivative of sine is. It's cosine, and I'm going to just put back the g, because the formula clearly calls for the derivative with g still plugged in. So that's what I have. The derivative of sine is cosine, and the point is still there. Now, the job is not done, because we have this times g prime. Usually I say derivative of the inside. So derivative of the outside times derivative of the inside, but whatever. So cosine, the derivative of the inside is just 2x. So all of this simplifies into 2x cosine x squared minus 1. Let's see. Another example, because we can. Okay, let's do one more example and then we'll do. So let's go with e to the sine x. Now, if you ask me why, I'm just going to say because I really don't have an answer why. It's what we call mathematical gymnastics, right? You do a problem that you can solve correctly, and it just ends there. You just walk away. So what is the outer function? What's the boss? E is the boss. So that's my f is equal to e to the x, and g is going to be sine x, right? So when you take this and plug it into the exponent of the e to the x, right? Plug into x, which is exponent, you will immediately see that you are getting this thing back. So now the formula says take the derivative of e to the x or e to the sine x, whatever it is going to be itself, right? That's what these functions have to bring. And then times the derivative of g. What's the derivative of sine x? Cosine x. Need to get you guys microphone because let me see who had dinner is going to be designated person to shout the answers. You please, by all means. All right. There is no other way to do this problem, guys. Do you see that? Right? There's no other way to deal with this other than the way we did. It's not a product rule. It's not a quotient rule. It's just, it is the derivative. So, and we are learning the new technique. So there you go. Let's take a look at the other notation and make sure that we can make sense of it. So let's go with another problem. ln of x squared minus 1, huh? Sounds good. The beauty of these lectures is you can just literally throw anything on a table and you can just make functions off of it, all right? So that's great. I have this function, and it's going to be ln and x squared minus 1. We should quickly agree on what f is and what g is. What's f? ln x, that's the boss. And x squared minus 1 stays as g. So now what do I have? I have the derivative of ln of x squared minus 1, which is equal to okay. So now it's ready. It's ready for the derivative right there. So what do we do? Well, the derivative of ln. Oh, we didn't cover the derivative of ln. How about a little bit ahead, huh? Just because we can. It's going to be x squared minus 1 over, and then the chain rule kicks in, and it's 2x on top because that's the derivative of the inside of the thing. I don't know, probably you will argue that polynomial derivatives are easy, right? The derivative of x cubed is 3x squared. So yeah, you can argue that, sure. The interesting thing for me over here is to realize that to find these derivatives for ln, you just literally go copy, paste, and put its derivative on top. Go like that. If it's ln. If it's any other base, there's more work to be done. So this was, yeah, I was steering away from ln earlier, and now here it is, and yeah, it's all wrong. No, it's not wrong, I'm just kidding. Okay, so now we have, what do we have? We have the rule. Well, let's do another example, and I'll write the rule underneath. So the derivative of square root of x squared plus 3. The derivative of the outside, and f is equal to x and g, sorry, x squared plus 3. No, what am I writing? It's square root of x. Wow. And g is x squared plus 3. Nice. So when we take the derivative, we take the derivative of square root of x, and that is 1 over 2 root x. So right, that's the derivative. So now what is the derivative here? Well, it's going to be 1 over 2, and then the square root will have the g, and then all of that times the derivative of g, which is simply 2x. So now these guys cancel. There's not that much as you can do here. You get 1 over square root of x squared plus 3 times, oh, I can just put x here. I was about to say time x, but I can just put x there, and that's that. So this will be the derivative of this composite function here. If you are not that great with these calculations, all you need to do, guys, is to practice how to decompose. So FG, FGH, FGH, whatever the next letters are, you can pick whatever you want. So what we discovered so far is that every time you had a function composition, the piece of calculation that kicked in is the extra you haven't seen so far, and that's, in this case, 2x over here, 2x over here, then you have cosine x over here. So they show up every time. They have to. They show up every time. So what should we do? Well, you can have as many of these functions nested, right? As many as you want. Generally, on exam, you're going to run into 2 or 3, but no more than that. 2 or 3 layers. That's enough to show your chain rule superiority. So what can I do here? The derivative of, is there anything I didn't use so far? 5 over x to the 6. I'm trying to see how can I make this worse. Yeah, that's what I'm doing. Oh, I know. Here. 3x minus 1 to the 6th power. Beautiful. See? It worked out. So anytime you have the problem that doesn't look like it's a standard thing that you've seen, try to, work around it a little bit to put it in a form that you would like. So now ddx as instructions outside. I could have moved the 5, but it's going to create confusion, so I'll leave it there. And I'm just copying now. So this is 5 divided by 3x minus 1 to the 6th. I can't hear you. There is no quotient rule here, right? This is simply, well, this is what I want to show you. So my hope is that you will go, oh, and well, let's see. So now I'm going to make another move. Maybe I can finally kick the 5 outside. There we go. So where am I? So this is 5, and look at this, times 3x minus 1 to the negative 6. So it's much easier to deal with this than to deal with function. And it's much easier to deal with the product rule, with the chain rule, than with the quotient rule, because quotient rule is just one big mess of the formula. So, oh wait, I doubled up on 5s. No one said. Yeah, I doubled up on 5s. I already kicked the 5 outside. So, take it out of the purse? Is that what you said? Did you say take it out of the purse?
I said kick it out of the purse.
Oh, kick it out of the, okay. It's pretty much the same thing. So, now, observe that I have my function composition where f is equal to what? What happened?
X negative 6.
No, I'm just looking for f, and then tell me g as well.
3x minus 1.
3x minus 12?
Minus 1 over negative 6.
How'd you come up with that?
I got answer. Is it negative 90 over 3x minus 7?
We first take a look at the decomposition, and then we're just going to do it easily, right? So I have x to the negative 6 as the boss, and 3x minus 1 is g. So now my derivative of x to the minus 6 is actually x to the minus 7, because it picks up a power. So we need to integrate, and I'll kick 5 outside. 3x minus 1 raised to the negative 6 dx. Is this the first integral I'm doing?
Yeah.
Wait, why did I write the integral?
Why are we?
Yeah, the derivative. Holy.
I was like, what?
Because he's asking me for every single class, because he's in chapter 5 already, and every single class he has another integral. He's doing it right. It's just that, you know, and then I stick inside, and it's all right. So, so what is this? It is negative. Oh, I forgot the 5 now. Great. You know what? Let's go home. So copy the 5. We have a negative 6. Guys, this is just a simple, right? Drop down the power and then minus 7. So we have 3x minus 1 to the negative 7, and then times the derivative of the inside, which is 3. So we started with something that it looks like we could use quotient rule, right? But you see that to the 6, actually? Yeah, it doesn't make it for a nice quotient rule. It's actually tougher quotient rule. But when you rewrite it, I wrote like this 15 times for no reason. Like this step is the same as this step, and then whatever, this step is the same. I give up. Over here, you have copy, which is the constant. You have the derivative f prime with g plugged in, and you have your g prime. There we go. Right? So no copy. So these are the things that we have. Now 6 times 5 is 30 times 3, so we have negative 90. And we have 3x minus 1 to the negative 7. And if you want to make this into a nice fraction, that's what we have. Negative 90 over 3x minus 1 to the 7th power. So what I did is I used the chain rule with a simple algebra, just algebra manipulation, where I took the denominator and put a, oh, I know what I did. You didn't put that, I took 5 out. And now I see 5 goes up. The whole step for that. All right, good. I'm going to put, let's say, 2 of these for you to enjoy, and then we'll continue exploring these markers instead. Let me see. I'm going to write the formula for chain rule on the board. So the derivative in respect to x of the function composition f of g of x is given as f prime of g of x times g prime of x. There you go. So that's our formula. And let's put 2 examples so you can try this now. So first example, let's go with, so we can't do ln's yet. We can't do inverse trig yet. Inverse tangent is wonderful. So let's stick with the trig. Sine squared of x, oh no. Don't worry about the square. Just sine of x cubed plus 4. That's good enough. And the second problem, ddx of 4e to the x squared plus 3. That's it. Let's see what you get. Meeting to talk about priorities in choosing a school. Like, who chooses a school? It's like walking in the cafeteria, it's like, wow. Hopefully we'll talk. Yeah, exactly. Hopefully we'll talk about it.
That's what I thought. I was like, I don't know if people know it yet.
No. You have two functions, you have two products, two things you have to do, right?
Yeah.
All right, let's take a look at these problems together. The first problem has two functions, right? There is f, which is sine x, and then g gets plugged in, which is x cubed plus 4. So derivative of sine is cosine, and we have to keep the same function, g. I call it guts, right? The guts, it's good? Perfect. And then times the derivative of guts, right? Which is 3x squared. Way to make the class terrible, right? I'm an expert at that, so yeah. So that will be the answer, right? We have the derivative of f with the g still plugged in, and then derivative of g, and we're done. We do the same thing on the next one. F is the outer function, which is 4e to the x, and then g is the inner function, which is x squared plus 3. And that will be the outer function, so the derivative of e to the x is still e to the x, so we just get 4e to the x squared plus 3 back. The entire thing, we get it back, because the derivative of e to the x is itself e to the x, and we are still supposed to have g plugged in. So it's literally Control-C, Control-V on that one, right? Times the derivative of the exponent, and that derivative of the exponent is just 2x. So 2 times 4 is 8, and the answer is 8e to the x squared plus 3. That's what I said, 8x. It's clearly 8x. I'm not sure. See, it's right there. That x that you're calling. It's right. It's x. Yeah, sure. Pay attention, please. Oh my God, people. Thank you. All right, good. Are you feeling at least a little bit confident with the basic thing? Because, you know, all right. This is when when the chain rule starts becoming interesting, right? Lock the doors. No one leaves.
So hypothetically, I could, when finding f prime g of x, I could just find the derivative of f of x, and then just replace x with g of x at the end.
Yes, and then times g prime.
Oh, so I could just find the derivative normally and then replace it at the end.
Yes. Good effort. Got it? Nice. All right.
Also chain rule, if we can use a chain rule for any equation, why do we
Very good. Disclaimer, we do not need quotient rule ever again.
X. I hated that.
Oh, you hated them? So yeah, quotient rule is completely pointless after this. But we have to get there actually. We did that one function that algebra fixed, but we're going to get in much better shape with a quotient rule. All right, now next level. Next level is when you don't have only two functions, right? One plugged into another. You have a function plugged into a function, plugged into a function, plugged into a function, because let's be fair. F composed with G, composed with H, composed with K, composed with J of X, and then you close it, right? We can do this mathematically. You can string as many of these as you want, right? And the chain rule needs to be able to take care of it. And you know what? It will, like this. Before I go and do this layered chain rule, I'm going to go back and remind you with my trusty pink highlighter that we had two functions and we had two factors. We had two functions and we have two factors. It's always like that. So now, if I have four nested functions in a chain rule, common sense would say you better have the four factors in your answer. This silly thing serves as the title of the layered chain rule. So this is where I'm going to go back to that sine squared x cubed plus 8, whatever. And I'm going to ask you, how many functions do I have on a pile over here? 3 functions, very good. So, and here's the $1 million question. What is the boss function? X squared, there we go. X squared. Please remember that sine squared x is actually this, right? So yeah, x squared is the boss function. And then sine, and then x cubed plus 8. So f is going to be x squared, g is going to be sine x, and then h is x cubed plus 8. And you can actually now plug these things in So this will plug in here, and then you will take the whole thing and plug it in there, and you got it. Does it make sense? So when you decompose this on the side, and yes, you are going to have 3 or 4 functions, and yes, on the exam as well, right? You can check on the side when you are done, or what plugs where, and then you get. So now, what is the response for chain rule here? The response is the derivative of x squared is 2 times the derivative of the inside, which is sine. Now, this is the tough part to see. This used to be, I'm going to erase this. Please look at the screen. This used to be sine squared. You drop that in front, and then 2 minus 1 is 1. So you see that the entire function is inside. Now we go times cosine, because the derivative of sine is cosine, and we still have to put x cubed plus 8, right? Times, again, the derivative of the inside, which is 3x squared. And now if you ask me, what prevents me from going another derivative from 6x, another derivative for 6, and then finally all other derivatives to infinity are 0, which would make every chain rule 0, right? I say what prevents you from doing that is the fact that you had 1, 2, 3 over here, you have 1, 2, 3 over here. That's it. You ran out of functions to take derivatives off. It's a derivative per function. Yeah, they're nested, sure, and you have to figure out the way it works. But 3 input functions, 3 derivatives are multiplied in some sense as factors in the answer. Now, you can make this prettier by, figuring. So we have 6x squared. Ooh, we can really do good job. Hold on. I am not going to use. I'm not going to use 2, because what is 2 sine cosine? What is this 2 sine x cosine x equal to? Nope. Did I just hear someone say 1? Thank you. Sine of 2x. Beautiful. Sine 2x. Come on, guys. You're pretty rusty. Who's going to calc 2? No, you aren't. I was waiting for those hands to go up. You don't know this identity, please don't sign up, all right? It's not gonna be beautiful. So here I have my 2 sine x cosine x. So the entire thing can collapse into sine 2x cubed plus 8. And then we still have, I'm just going to put this 3x squared in front. Oops, I forgot that. And that's it. That's the simplified version. I'm also going to underline this red, so it's a different kind of red. There we go. Perfect. So trig identity made it to. Now, please note, guys, that simplifying this in such a way reduces the amount of calculations that you are doing. If you're a computer science major, you have to live by this rule. You do not want extra calculations for no reason. That is slowing down your software considerably, right? If I am able to cut the amount of calculations that the processor needs to do by a factor of 2, I just made the speed of the software by a factor of 2 faster. Because less work is being done, the answer is there sooner. So if I cut out the times 2 and the entire one of these of calculations into a single sign, which picked up one more operation, I practically cut this calculation in half. And that is creating the efficiency. So if you're computer science, your ability to do algebra and simplify so that you have the smallest possible amount of calculations, you'll learn this when you take your appropriate classes. But I don't really have anything to kind of tell to mechanical engineers like, yeah, you really need to simplify this because the bridge is not going to hold. Yeah, it will hold. It's just you have to spend longer to calculate things, right? But for computer science, this is directly your life right there. Simplify, 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 the least amount of calculations to be done. And that leads to the fastest possible software. All right, so let's see. The derivative of we haven't done anything with tangent, so I feel like sad or something. Tangent cubed of, what should we put here? I know, e to the x squared, why not? You want to sleep tonight here? Look at this, terrible. All right, good luck, go. And if I put something like this on a test, I immediately have to make sure that I have enough money on the account for new set of tires. I mean, that's the bottom line, right? A few of you are already eyeing me on this one. And it's not even exam time yet. I understand when I cross the line, but that's it. Work fast.
Times 10 b times 8x squared. Now, 6. Yeah.
Okay, let's take a look at this. So how many functions do we have over here? 4 functions. Let's find them. What is the boss function f? X cubed. Very good. So you are hunting for this square or a cube on a tangent or something. That has to be the boss function. And then the first layer in is
10x.
Tangent x. Very good. And then the next one in, h? E to the x. Very good. And w, let's say? X squared. So now, x squared replaces the x in e to the x. It becomes x squared. Then e to the x squared goes for x in the tangent. And then everything gets cubed. And we're happy. 4 functions means you do 4 factors of derivatives, and then you quit. All right? So x cubed, that's 3x squared. Are we all clear on 3x squared? Now, what is that x?
Tangent e to the x squared.
Yes. Now, we have times The derivative of tangent is secant squared of e to the x squared. Nice. Times the derivative of ex squared. What is the derivative of e to the x squared? E to the x squared. Good. And then times 2x. Beautiful. Not much we can do here. We have 6x e to the x squared, and see, this e to the x squared is within secant squared, and this one is within tangent, so we can't really do anything with like factoring or anything like that. So I have tangent squared e to the x squared times secant squared e to the x squared, and e to the x squared, the rest is there. Yeah. Should I color code? We have a 3 and 2x giving us 6x. Then let's go orange for e to the x squared to the e to the x squared. And then the other two are easy and quick to see.
Oh, I see. Okay.
This square just went down on tangent. Yeah.
I keep hearing it's x squared. It's e x squared squared. It's bothering me.
What dictates the placement of e to the x versus x squared? If the parentheses were 1 more in, and it was over parentheses e to the x.
Yes, very good. So this is the question. What is the difference between e to the x squared and e to the x squared? Well, they're not equal. They're not equal. Because the one on the left is e x times x, right? Because that's x squared. And the one on the right is e to the 2 times x. Exponent of the exponent multiplies the exponents. So you are right. They are not the same. Later in this chapter, which is next week, when we do logarithmic differentiation and we do the derivatives of logs, we are going to encounter the same idea that we had, that sine squared x is sine x squared, then ln squared x will be ln x squared. The notation is consistent, right? And that all of that is different than clearly sine x squared there, which is squaring only the x. So while this one has sine times sine, this is sine of x times x. So they're vastly different.
And that would change the order of operations for the
Yes, it will. Yes, it will. Any other questions, just questions? Concerns you'll have to address when you do the homework. Wow, this clear? Well, let's go to the next level, by all means. Now you're probably saying, all right, we just had a chain rule that had 4 functions. How can you possibly make this worse? Like that. I'm going to invite the product rule and chain rule and quotient rule to join us with the chain rule. And say, how about we have the chain rule within the product within chain, quotient with the chain, and product with the quotient together with the chain, right? So that the problem can be like 6 pages long and you miss a minus sign, it's just 0. Nah, it's kidding. But it does hit, right? It's like, wow, tough. So I mentioned, and the students actually mentioned that they were fresh from differential equations. They said, oh, we did damped oscillations. I said, yeah, that was exactly the e to the negative x I mentioned with the sine and cosine following it. So what we can do now is we can combine all of these rules into a problem. Obviously, it will be very, very bad to have all three in any of the problems, but it's doable, obviously. But you know, plus the only reason why we will do something like this is mathematical gymnastics, because I don't know of applications that would require so many of those rules on a pile, right? So let's take a look at this problem. So the derivative of x squared e to the sine x. X squared e to the sine x. So I need you to tell me, what is this problem? What do you think? No. Well, I just want to know which rule do I need to use. That's my question. All I heard due to air conditioning is that's it, and I can't really make it out of what are the answers. So if anyone, product rule. Thank you. Yes, guys, this is a product rule question. That's it. It's a product rule question. You have function f and function g. F times g. That's it. This is a product rule question, end of story. Now, eventually you will have to take the derivative of this in a product rule formula. And then what kicks in? The chain kicks in, exactly. So, I'm going to go, first I'm going to write product rule. Because we have the derivative of f times g, right? So that's that. And then we are going to go and say, product rule, copy the first, derivative of the second. There's the chain rule right there, right? So, derivative of the second, which is e to the sine x times the chain rule cosine x, plus copy the second, e to the sine x, times derivative of the first, which is 2x. So now let's write what's what. There's your f, there's your g, there's your f, there's your g prime, there's your g, there's your f prime. Green? Copy the first, derivative of the second, plus copy the second, derivative of the first. All right? Computer science, let's go. We are factoring this as far as we can to reduce number of operations. We have e to the sine x and x that can be kicked out. What's left is x cosine x from the first term, plus 2 on the second term. Less calculations, obviously, in the simplified version than in this. So, what is this question? It is the product rule question. And then, so, such is life. Right? You had to do this, which was the chain. So this is chain within product, but product rule was the main technique. All right, next one. Find the derivative of what? Of something interesting. Let's go with, let's go with one of those functions for, so e to the negative 3x times cosine of 4x. What is the main rule? Product rule again. It is exponential times cosine. What would this look like if you graph it? We talked about this briefly, right? It's a cosine, so it's going to start on top over here, and then it's going to and eventually die. So that's what we have. This would be your y, this would be your x. Now you can actually replace this x with t, and then it's time, and that's actually what you need to have, but whatever. All right. Product rule. Copy the first one, e to the negative 3x times the derivative of the second one. Derivative of cosine is negative sine 4x times the derivative of 4, right? The derivative of 4x is 4. So that's our chain rule right there. Plus, copy the second, cosine 4x, times derivative of the first, which is e to the negative 3x, times the derivative of the exponent, which is negative 3. So now we have negative 4e to the negative 3x sine 4x minus 3e negative 3x cosine 4x. We can kick out negative sign and e to the negative 3x, which leaves us with 4 sine 4x plus 3 cosine 4x. There are further mathematical manipulations that you can do to combine this into a single, but whatever. No coffee. So here we have next example. Yes. What happened?
Like the front of that.
Yeah, e to negative 3. Yeah, because I had one here and one here. In both terms I had one each, right? So just kick it out. What is the derivative of sine of x squared e to the x? What's this? Come on, say it. Can anyone tell me what this is at least before we do it? It's chain rule, yes. This is a chain rule problem. And then when you do the derivative of the inside, the derivative of the g prime, you have a product rule to worry about. So the boss function is sine, and then the guts, right? The g is x squared e to the x, and that will be product rule when you have to take the derivative of it. So this is completely reversed from previous problem when you had to do product first and then chain when you had to. Now you're doing chain, and then you will have to do product rule when you put that derivative. So you can still, let's say, f is equal to sine x, g is equal to x squared e to the x, and then you will still know that this is uv. Right? So the derivative of sine is cosine of x squared e to the x, and now times, and I have to have a product rule here. And the product rule is copy the first, x squared times e to the x derivative plus e to the x times 2x. I can kick out x e to the x cosine x squared e to the x. What's left is x plus 2, right? Is that good? All right, fine. Now, if you started panicking by now, where's my quotient rule? Here we go. I mean, I do not want it to feel left out or something, right? So we will have the quotient rule set up as, say, sine x squared divided by x plus x cubed plus 1 cubed. I know that everyone was holding their breath. No exponent on that one. it has been communicated to me to put that exponent there. Here's your caution rule, since you are asking about it. After this example, we're going to do only one more calculation and we're done. All right, great. Okay. So let's take a look at this problem together, then do that one calculation and be done. Quotient rule. Experience, right? We take denominator and we square it, so that's going to be x cubed plus 1 to the 6th power. And we have x cubed plus 1 cubed. Now I need to take the derivative of sine x squared. That's cosine x squared times 2x is a chain. Because the derivative of sine is cosine and it was x squared, so it's not sine x, it's sine x squared. So I need that 2x in a chain. minus copy sine x squared, and then take the derivative of the denominator, which was 3x cubed plus 1 squared, times the derivative of the inside, which is 3x squared. Now we are able to cancel and get 4 of these. So let's see what's left. We have 2x, x cubed plus 1, cosine x squared minus 9x squared sine x squared divided by x cubed plus 1 to the 4th power. It's not worth factoring because all I can factor is 1x. So that's that. Just leave it there. Ready for the last calculation? I know, right? It's amazing. So we said no need for quotient rule anymore. We learned everything we need, right? So if I have the derivative of f over g to be given as gf prime minus fg prime over g squared, we can opt instead for the derivative of, instead of the quotient, we do the product, f times g to the negative 1. Not an inverse. That's a little bit bad in mathematics that we have the inverse as the same notation as x to the negative 1. Such is life. So to illustrate this, we're going back to the very basic quotient rule problems, which will eventually turn into a chain rule problem. So say I have the derivative of sine x divided by x squared. That's it. The only thing that is going to happen is going to be, I'm going to change it into a product. So I have sine x times x to the negative 2. And now we run the product rule. So derivative, so copy the first, sine x, derivative of the second, it's negative 2, x to the negative 3, plus x to the negative 2, derivative of sine is cosine x. Now we have negative 2 sine x over x cubed plus cosine x over x squared. And I will multiply the second term by x times x to make common denominator of x cubed. So I have negative 2 sine x plus x cosine x divided by just x cubed, because now it's common denominator. Ta-da! Can you imagine? That's it.